Here is a number that should not exist. 2,200 megapascals of tensile strength sitting inside a mass-produced car body, 30% lighter in the panels where it counts than the steel it replaced. You heard that right. Stronger and lighter at the same time in the same sheet of metal. For 100 years, that combination broke every rule of steelmaking. And that is just the beginning, because this steel almost never made it out of a Chinese research lab in 2009, and the reason it did is stranger than the number itself. If a material that breaks its own physics sounds worth 6 minutes, hit a quick like and subscribe so you do not miss the next one. By the end of this video, you will know exactly how China quietly solved a ceiling the rest of the world's steelmakers had accepted as permanent. For most of the last century, steelmakers lived by one unbreakable rule. Make it stronger, and it gets harder to bend. Make it easy to shape, and it cannot take a real hit. Engineers call this the strength-ductility trade-off, and every major steelmaker on Earth, ArcelorMittal in Europe, Nippon Steel in Japan, POSCO in South Korea, built entire product lines around accepting it as physical law. Textbooks taught it. Purchasing departments planned around it. Nobody expected it to move. Here's what that rule actually looked like on paper. First-generation advanced high-strength steel, the dual-phase and trip steels that have framed car doors and pillars since the 1980s, tops out at a strength times elongation product under 15 gigapascal percent. That number is the industry's own scorecard for how much strength and bendability a steel can deliver at once, and 15 was close to the ceiling. Push past it, and the steel that could survive a crash could no longer be stamped into a door panel without cracking. Engineers had a name for that failure. They called it edge cracking, and it showed up right when a factory tried to push tonnage and safety at the same time. There was a second option, and it made the trade-off worse, not better. Second-generation AHSS, TWIP, and austenitic steels actually broke the ceiling, hitting strength ductility products above 50 gigapascal percent. But getting there meant loading the alloy with manganese and other elements at multiples of normal levels. That drove up cost, complicated every stage of production, and made the steel nearly impossible to weld reliably at scale. Decades after it was developed, second-generation AHSS still barely exists on a real assembly line. It is a laboratory success story that never became a factory story, so automakers were boxed in. Stay with first-generation steel and accept the weight penalty. Reach for second-generation steel and accept a price tag few manufacturers could justify. Or walk away from steel entirely and pay a premium for aluminum or carbon fiber composite panel by panel across an entire vehicle body. None of those three options solved the actual problem. They just chose which cost you were willing to absorb. Think of it like a rubber band stretched next to a steel cable. One gives you flexibility with no real strength. The other gives you strength with no give at all. Tie them together, and you still have two separate behaviors sitting side by side, not one material doing both jobs. For 100 years, nobody had found a material that behaved like both at once, and the entire global steel industry had quietly stopped looking. The ceiling had been there so long, it stopped looking like a ceiling. It just looked like physics. But somewhere outside the spotlight, that search never actually stopped. And what came out of it was stranger and far earlier than anyone in the industry was prepared for. In 2009, inside a research lab in Beijing, a team at the China Iron and Steel Research Institute, led by academician Wang Yuqing, produced something that had no business existing on the strength ductility chart at all. It did not sit near the ceiling. It sat past it, in a space the chart had never bothered to draw. They called it a third-generation automotive steel, and on paper it looked like a typo. Tensile strength roughly 4 times that of first-generation steel. Elongation of 35%, enough bendability to stamp into a complex door panel without cracking. And here's the detail that puts everything into perspective. The alloy content was less than a third of what second-generation steel required, which meant the cost stayed close to first-generation pricing instead of ballooning into second-generation territory. On a single spreadsheet, it beat both existing generations of steel on the 2 numbers that mattered most, and matched the cheaper one on price. Most people who read about steel breakthroughs never get past the headline number. The part nobody covers is how quietly this one moved. There was no press conference, no international unveiling, just a lab result that sat for over a year while metallurgists elsewhere kept building product lines around a rule this steel had already broken. Nobody outside a small circle of Chinese metallurgists even knew the ceiling had cracked. They said something similar about niobium a generation earlier, a minor additive, not worth restructuring an entire alloy strategy around. We all know how that ended. Niobium microalloying became one of the defining metallurgical developments of the 20th century. In late 2010, Taiyuan Iron and Steel Company took the lab result and put it on an actual production line. Not a demonstration run, a real mill. They rolled out hot-rolled coil and cold-rolled sheet in thicknesses from roughly 1/10 of an inch up to just over 1/2 an inch. On February 21, 2011, the China Iron and Steel Research Institute made it public, with commercial-scale production targeted for 2014. The gap between the lab result and the public announcement was more than a year, and that gap was not wasted time. It was the industry quietly checking whether the number would survive contact with a rolling mill. Here is the brutal catch: a lab sample proving a number is possible and a steel mill proving that number can be produced, welded, and shipped by the ton are two entirely different problems. The 2009 result only mattered because someone was willing to spend the next several years finding out whether it would survive contact with a real factory floor. But the number itself, 4 times the strength, 35% elongation, still needs an explanation. What actually happens inside this steel that lets it behave like two contradictory materials at once? That mechanism is where the real story starts. Picture wet sand at the edge of the ocean. Walk across it and your foot sinks in. Loose, soft, no resistance at all. Now stomp on it hard, and for an instant it locks solid under your heel before your foot breaks through. The sand did not change. The way it responded to force did. That is roughly what is happening inside this medium-manganese steel, and here's what most people get wrong about it. They assume a stronger steel just has more of something, more carbon, more alloy, more mass. This steel does not work by having more of anything. It works by holding a fraction of its internal structure in a soft, metastable phase called retained austenite, deliberately left unstable, waiting. Metallurgists spend careers trying to eliminate instability from a material. This steel was engineered to keep a piece of it on purpose. While the steel sheet is being stamped and shaped at the factory, that soft phase stays soft, which is exactly why the metal can bend into a door panel or a pillar without tearing. But the instant real stress hits it, a crash, a sudden impact, that same soft phase transforms on the spot into hard martensite, precisely where the force lands. Metallurgists call it transformation-induced plasticity, or TRIP. In plain English, the steel decides how hard to become, and it decides in real time exactly where it is needed. Nowhere else on the sheet does anything change, only the exact spot taking the hit. This is not a theoretical mechanism. In pilot production, this medium-manganese steel line hit tensile strengths between roughly 650 and 850 megapascals while holding 30 to 40% elongation. Numbers that, a decade earlier, metallurgists would have told you belonged to two separate families of steel that could never occupy the same sheet. The steel is not strong. The steel becomes strong on demand in the exact spot that needs it. Compare that to ordinary steel, which is stamped once, tested once, and then simply hopes the number on the spec sheet holds true on the worst day of a driver's life. This medium manganese steel is still making decisions on that worst day, long after it left the factory. But solving the strength-ductility problem does nothing for the next wall the steel was about to run into. Because to push tensile strength past 2,000 megapascals, the range automakers actually wanted, this steel would need to be stamped at temperatures near 1600 degrees Fahrenheit, and the protective coating required to survive that heat came with a problem nobody in China had been allowed to solve. Here's the detail that engineers rarely admit in public. For more than a decade, the aluminum silicon coating needed to hot stamp ultra-high strength steel above 2,000 megapascals was locked behind an exclusive patent held by a handful of European steelmakers. Domestic automakers who wanted it had to import coated steel piece by piece and pay licensing fees on every single ton. It was not a technology gap, it was a paperwork wall, and paperwork walls do not respond to better engineering, until somebody finds a different door. And here is where it gets uncomfortable. That same coating, the one required to keep the steel from oxidizing during 900-degree forming, was also making the finished steel more brittle. Solve the heat problem, and you created a toughness problem. Every fix seemed to trade one failure mode for another. It was the strength-ductility trade-off all over again, just wearing a different coat. A team at Northeastern University's National Key Laboratory of Rolling Technology and Automation went looking for the actual cause, instead of accepting the trade-off as fixed. What they found was carbon quietly enriching itself at the exact interface where the coating met the steel underneath. A microscopic buildup that was the real source of the embrittlement, not the aluminum silicon coating itself. For years, engineers had been blaming the coating for a problem the coating was not actually causing. Here is the part that changes everything. The obvious fix would have been a thicker coating, more protection layered on top of more protection. The team did the opposite. They engineered a thinner coating with tightly controlled carbon distribution at that interface, a thinner protective layer, outperforming a thicker one. It sounds like it should not work, and that is exactly why it does. The resulting product line, branded Aluslim, spans 1,000 to 2,200 megapascals and tested 10 to 20% tougher than existing global coated products at equivalent strength levels, while eliminating a licensing dependency that had cost Chinese automakers money on every ton for over 10 years. 2 separate labs, 2 separate walls. Neither one had anything to do with the other on paper. One was about internal steel chemistry, the other about a coating a few microns thick. But putting both inside a single sheet of steel and getting that sheet onto an actual assembly line was still not solved. That problem belonged to a steelmaker, not a research lab. A steel that behaves like 2 contradictory materials and a coating that gets tougher by getting thinner are both genuine breakthroughs. Neither one means anything to a driver until a steelmaker and an automaker agree to build an entire production line around combining them. A discovery sitting in a journal does not stop a single crash. Only tonnage rolling off a real line does that. For over a decade, the old approach for Chinese automakers looking for ultra, high-strength coated steel was importing it, piece by piece, from a single overseas supplier, paying a per-ton licensing premium the entire time. That was not a supply chain. That was a dependency, and it sat quietly inside the cost of every vehicle built on top of it. Manchin Iron and Steel changed that equation directly, co-developing with Xiaomi Auto and Great Wall Motors' Wei brand a 2,200 megapascal aluminum silicon coated hot-formed steel that combined the medium-manganese strength mechanism with a thin, high-toughness coating, built from the outset for mass production, not lab demonstration. In 2025, the China Iron and Steel Industry Association gave the material its Special Product Development Award. This is where the mainstream coverage usually stops, treating it as one more industrial award. Here's what most people miss. This was not a handful of prototype panels tested in a lab. It was not one demonstration vehicle built to prove a point at an auto show. It was a full production commitment, where 73.7% of the entire body structure of the Xiaomi SU7 now uses high-strength and hot-formed steel, with this exact 2,200 megapascal material carrying the core crash structure of the vehicle. The lab result from 2009 and the coating breakthrough from Northeastern University were no longer 2 separate stories sitting in 2 separate papers. They were riding down a highway inside a car people were actually driving. A discovery that once existed only as a graph in a metallurgy journal was now absorbing real impact energy on real roads, without the driver ever knowing the sill beam beneath them had a 15-year backstory. But a number this large, applied at this scale, could not simply be announced and trusted. Before anyone could call it certified, it needed independent crash data. And that verification is where the real payoff of this entire story lives. Here is the honest picture. This steel is remarkable, but it is not magic, and the certified numbers behind it deserve to be stated precisely rather than rounded up for effect. Applying the 2,200 megapascal steel to the Xiaomi SU7's body sill beam cut that single component's weight by 15%, while reducing side impact intrusion by 20%, a case where lighter and safer moved in the same direction instead of fighting each other. Compared with the 1,500 megapascal hot-formed steel it replaces, panel thickness can drop 20 to 30%, individual components lighten by 15% or more, and a full vehicle can shed up to roughly 44 pounds without enlarging the battery pack or shrinking cabin space. Not one trade-off traded for another. Weight down and protection up on the same component at the same time. That number matters more than it sounds. China Automotive Technology and Research Center data ties every 22 pounds of weight cut on a new energy vehicle to an additional 6 to 8 kilometers of range, alongside a drop of roughly 0.3 kilowatt hours of energy use per 100 kilometers. 44 pounds off the body is not a rounding error on a spec sheet. It is real driving range without adding a single cell to the battery pack. And this is the number nobody talks about. Independent 20 to 24. Testing by the China Insurance Automotive Safety Index found that vehicles using 2,000 megapascal plus hot form steel in their core structure achieved the top rating for cabin integrity in every single case tested, with several models avoiding post-crash battery fire entirely. Vehicles built on steel below 1,500 megapascals passed the same two tests only 72 and 81% of the time. That is not a marginal safety improvement. That is the difference between a cabin that holds its shape and one that does not, in the exact moment it matters most. Here is the honest trade-off. This steel costs more to produce than what it replaces. It requires hot stamping tooling most mills do not yet own, and it does not end the industry's parallel push into aluminum and composites for other weight-critical panels. It solves one problem completely. It does not solve every problem. The ceiling did not move a little. It moved past the point most of the industry had treated as physically off-limits. If that surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. Every electric vehicle on Earth is fighting the same equation: battery weight against crash safety against range, with the body structure caught directly in the middle. That is not a China-specific problem. It is the defining materials engineering question for the entire global auto industry right now, and it does not care which factory a car rolled off. The sectors this touches go well beyond one car brand. Global automotive body engineering, battery enclosure design for electric vehicles, and increasingly heavy truck and commercial vehicle structural steel, all of which face the identical strength versus weight math. Anywhere an engineer is trying to cut mass without cutting safety, the same trade-off is sitting on the table. Adoption is not simple. It requires hot stamping presses capable of forming steel near 1600 degrees Fahrenheit, retooled welding lines built around the thinner coating chemistry, and quality control systems designed specifically around that carbon-controlled interface. None of that drops into an existing steel plant overnight. A mill cannot simply order the new alloy and start shipping panels the following week. Industry reporting already shows 2,000 megapascal steel becoming close to standard in vehicle bodies, with 2,200 and even 2,400 megapascal grades now entering production elsewhere. Here is the historical parallel, and it is worth sitting with. Niobium microalloying was treated as a minor additive when it first appeared in steelmaking last century. Materials researchers who study exactly this kind of steel evolution have since called it one of the most important physical metallurgy developments of the entire 20th century. Breakthroughs in this field rarely look important on the day they happen. They look important only once every mill on Earth is quietly using them. The genuine technical advantage here is not the strength number, and it is not even the patent. The part that is actually hard to copy is the interface chemistry. The precise control of carbon distribution at a boundary a few microns wide. That is process knowledge, built through years of failed attempts, and it does not transfer just because a patent eventually expires. A competitor can read the paper. A competitor cannot skip the years of failed batches that taught this team where the carbon was actually hiding. The limit that held for over a decade was never political, and it was never about which country could outproduce another. It was a carbon diffusion problem inside a coating a few microns thick, sitting on top of a steel that most of the industry assumed could never be both strong and bendable in the first place. Someone finally solved the actual chemistry underneath it. If steel that hardens itself on impact caught your attention, there is a Chinese metals breakthrough that takes the same idea somewhere even stranger. A self-healing metal that repairs its own internal damage after the fact instead of just resisting it in the moment. I already covered it in China's insane self-healing metal breakthrough will change machines forever, and once you understand how this steel earns its strength, that one is going to feel like the natural next step. Here is the actual size of what you just watched. This was never really a story about one car's sill beam. It was a test of whether steel could remain the backbone material for a world rapidly moving to electric vehicles, or whether the future belonged entirely to aluminum and carbon fiber composite. For a decade, that question stayed open. This steel just answered it, quietly, on a production line most drivers will never see. If you made it this far, you now understand more about how ultra-high-strength automotive steel actually gets built than most people who write about electric vehicle safety for a living. Here is what was actually proven. two separate breakthroughs, from two separate institutions over a decade apart, a medium manganese steel that hardens itself on impact and a coating that gets tougher by getting thinner, had to be discovered independently and then physically combined on a single production line before either one meant anything to a person driving down a highway. Neither lab could have gotten there alone. A steel that decides how hard to become, wrapped in a coating that protects it by doing less, not more. That is the whole story, compressed into a sill beam most owners will never think about again. If this changed how you think about what just steel is capable of, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. As EVs keep getting heavier because of their batteries, do you think steel keeps winning this fight against aluminum and composites, or does the industry eventually leave steel behind for good? Let me know below. I read every single one. See you in the next one.